Hi, and welcome to Becoming Multiplanetary. I'm RichLB, your host for this episode, and I'd like to take this opportunity right now to let my co-hosts introduce themselves. Let's begin with Mikko.
Hello, I'm Mikko and I host the Deep Dive Fridays, and I'm quite eager to hear more about Mars Direct 3, and I'm going to hand over to Kage.
Hi everyone, I'm Kage, sometimes called Kage. I'm also one of your co-hosts today. Now I will hand over to AnotherSpaceNut.
Hi guys, I'm AnotherSpaceNut, a regular voice on this podcast. Looking forward to our next speaker, our guest speaker, Miguel. Would you like to introduce yourself?
Yes, thank you for the invitation. My name is Miguel Gurrea. I'm from the Mars Society Spain. I'm a collaborator there. And I'm here because of my recent presentation of Mars Direct 3.0, which is an architecture I proposed based on work by SpaceX and Robert Zubrin to hopefully be the architecture used for the first Mars mission.
Returning to us again this week, we have the Angry Astronaut. Would you like to introduce yourself, Angry?
Hello, I'm the Angry Astronaut, probably the most obnoxious commentator on YouTube when it comes to space channels. Very glad to be here and to hear about Mars Direct 3.
And last but not least, we have our nuclear specialist on the show with us this week, Framric. Would you like to introduce yourself?
Hi, I'm Richard, also known as Framric on Twitter. I'm a radiation protection specialist, been about 30 years in the nuclear fission industry, and I'm a total space geek. I'm very pleased to be here today on the show. Thank you for inviting me.
This week, we're going to be talking about the work that Miguel Gurrea has been doing, which is Mars Direct 3.0. So, Miguel, would you like to take a few minutes and explain to us and the listeners what Mars Direct 3.0 is in a nutshell?
Thank you. Well, Mars Direct 3.0 attempts to use the technology developed by SpaceX for the first Mars mission because SpaceX has focused most on Starship, which they've been developing for the past years. But they have not actually commentated in-depth plans for what to be done on Mars once the ships are landed. Mostly the only thing they have said is that they will use in situ Mars resources like water and CO2 to produce the fuel to return, and that's pretty much it. So I actually took some concepts from the original Mars Direct architecture proposed by Dr. Zubrin, then also the mini-starship which he proposed in Mars Direct 2.0, which was a revision of SpaceX's plan, and also some original ideas, and I combined them to produce Mars Direct 3.0. I'm sure they will have the presentation on the description if you haven't watched it already. There I go more in depth on all the plans. I have named each of the 4 ships going to Mars with the names of Spanish ships, the ones that were used to discover America, and the ones used to do the first trip around the world, for them to be more recognizable, and because I think it's a cool concept to have the names of these ships to discover the new world.
So I myself have seen your Mars Society presentation on Mars Direct 3.0, and I think it's wonderful. With your permission, I will include a link to your presentation in our episode description, if that's okay with you.
Of course. I will also be making a video before the year is out with HD animations and a few small changes that I've made, and it will be maybe a bit longer than the presentation because I was time constrained there. But yes, the presentation should be pretty much good for now.
Thank you, Miguel. Now, I would like to open questions up to our co-hosts. Anyone here have a question for Miguel?
Your plans of Mars Direct 3.0 are really fascinating, but they're also built on the history of 2 other versions, Mars Direct 1.0 and 2.0. Could you maybe go into a little bit of detail about what were those plans and what are the major differences between those and your latest iteration?
Yeah, sure. So the original Mars Direct was presented in 1990. I was supposed to be using a heavy launch vehicle, which is now the SLS, which Zubrin was actually on the panel that designed it. And it was just something similar to Apollo on Mars. This plan was actually written against the 90-day report, which was an incredibly expensive and complex plan to go to Mars using space stations and on-orbit assembly. It was all very complicated, so it was cancelled. So Dr. Zubrin wanted to make a plan that was simple enough for it to be affordable and efficient, and he was the first to seriously pose the idea of using Mars resources. And he wanted to use 3 ships for the mission. There were some other iterations like Mars Semi-Direct, but the idea that I think was the most important that he introduced was the idea of using the Martian atmosphere to obtain CO2, which would be split in oxygen and carbon. One of the ships would have taken hydrogen from Earth, and that hydrogen It would have been combined with the carbon to make methane, and then the oxygen would have been used as the oxidizer to produce the fuel for the return. Because taking all the fuel to the surface of Mars for the return, it's not impossible, but it's a huge task. You will require an amazingly huge rocket to deliver just a small ship that could return to Earth. So in Superman's original Mars Direct plan, only the hydrogen needed for the return trip was brought to Mars, which would be then combined to make methane, which would save a lot of mass and would make the trip actually viable. He tried his best to make this plan the NASA official plan to go to Mars, and unfortunately it never happened. So he created the Mars Society and wrote the famous book, The Case for Mars, which then inspired Elon Musk to create SpaceX, and then he presented their plan to go to Mars with a huge ship. But yes, they did not get very deep into what would be done once on Mars. The only improvement they made was, since Superman presented his plan, water was discovered on Mars. It was discovered there were large quantities of ice below the surface, which could be used to obtain the hydrogen via electrolyzing the water. And so they reached the conclusion that hydrogen from Earth was no longer needed. And then Superman actually made Mars Direct 2.0, which it's weird because it's not a revision of his original Mars Direct 2.0. It's actually a revision of SpaceX's plan, but he introduced the concept of the mini-starship, which is, instead of taking this huge ship to Mars, which would be very, very hard to refuel, he wanted to take a smaller ship to Mars, launched by the big Starship to Earth orbit, and then have that ship do all the trip. It will be cheaper in terms of power on the surface. I had some contact with Superman because we are organizing the European Mars Conference 2021. It was previously going to be this year, but we had the pandemic. I offered to debate him on his Mars Direct 2.0 idea because I initially didn't agree with it. I didn't see enough advantages in using the mini-starship. There was unfortunately no time in the schedule. But then I started thinking about it. For me, the biggest problems of using just a mini-starship instead of the Starship were that, yes, you can use less power to refuel, but you can also take less cargo to Mars. You still get a better deal because the ship is decoupled in Earth orbit or in transfer injection in the most complex version of his plan, but it's still not a huge improvement. And then I was actually surprised that Superman discontinued his idea in Mars Direct 1.0 of taking the hydrogen to Mars and went with digging or mining Martian ice. He says it's just 19th century industrial technology, and I agree that the chemical process, which is the Sabatier reaction and electrolyzing water, is very simple and doable. But I believe there are also more risks involved, like could they not find enough water? Could the machinery break? Because you're mining for ice, which would be turned into water, and water evaporates on Mars. There are no backup plans if that fails. So I believe that is a very dangerous part of the mission. So I did a few changes to Mars Direct 2.0. First change was, okay, let's bring the big Starship too, because Elon Musk has said they're planning on leaving the first Starships there, and have the bigger ship take all the cargo that's needed for the mission, including more solar panels than the mini Starships could carry, to make that more efficient. And then I rescued the idea of using the hydrogen brought from Earth, and I actually made it so it's inside of a big Starship, because hydrogen is very light, it's not very dense. So if you take the hydrogen need for the return trip on the mini Starship, it would occupy a lot of the volume. There would be almost no volume for the astronauts. So if you want an in-depth explanation, you can watch the presentation or the video when I make it, but those are the things that actually inspired me to do these changes.
That's really fascinating, thank you. You mentioned a lot of things there regarding chemical propulsion, so mining for ice, for example, and extracting oxygen and methane from it. And in the current Mars Direct 3.0 plan, all of the rockets are indeed using chemical fuel. In fact, in our last episode here, when talking with Angry Astronaut, we were discussing nuclear thermal propulsion. So what are your thoughts on nuclear thermal propulsion with respect to a Mars Direct plan, and do you think it's worth waiting for that to advance to increase the chances of success?
Well, I believe nuclear thermal is a promising technology. It's a pity that it was not continued, but it should be a great technology in the future. If Mars is actually going to be colonized, it will probably be very efficient to use nuclear thermal. But I tried to make the plan as simple as possible using the technology that SpaceX is already trying to develop. So, for example, there are no new engines that would need to be required for Master 3.0 than the Raptors. It's just the Raptor vacuum and the Raptor for atmospheric use. So that's it in terms of engines, which are a very expensive thing to develop. Nuclear thermal, I don't remember exactly how much power it has in terms of thrust. But what he said is that it's also very, very efficient to create the fuel on Mars. Because if you use nuclear thermal, you would probably need to take some fuel to Mars. If you produce the fuel on Mars and you calculate the total efficiency of fuel in terms of the fuel that you left on Earth, you get that it's very, very efficient to produce the fuel on Mars. So probably in the future, I think it's going to be a great technology to have functioning, but I just wanted to make it doable in the short to mid-term. That means using as much existing technology as possible. And I believe the Raptor system that's being developed by SpaceX is more than enough to do the Mars mission. And once it's done, and there's public support, and there's actually a base there, then a nuclear propulsion system could be rescued from the past, I believe.
So, Framric, we've heard here from Miguel about the mini-starships. As a radiation specialist, what do you think is going to be needed to be able to protect astronauts in a mini-starship?
Yeah, it's a good question. Thanks, Rich. The three basic principles of radiation protection if you're in a high radiation environment are time, distance, and shielding. The radiation levels as we start to head out of the Earth's atmosphere provides the equivalent of about 13 feet of concrete shielding. And as you start to head upwards, you're more exposed to cosmic rays. It's about 100 times higher when you're cruising at about 35,000 feet, the radiation levels, compared to sea level. About 1,000 times higher if you're standing on the surface of the moon without any shielding, and about 100,000 times higher if you're actually heading through the Van Allen belts. And one phenomenon is as you head up out of the Earth's magnetic field, which again provides protection, you get a lot more charged particles from galactic cosmic rays. You could end up with a solar particle event where stream of particles coming directly from the sun, and that all needs to be taken into account when it comes to protecting the people. Thin shells, aluminium shells or steel shells, can actually generate more radiation. The charged particles hit into them. It's called braking radiation, Bremsstrahlung, and you get a flurry of X-rays that can actually increase radiation levels. So going back to those basic principles, time, distance, shielding, well, the best way of protecting an astronaut going from Earth to Mars is actually to do it quickly. Spend less time in the interplanetary space, get to Mars, work on your shielding there with, burying a base or providing some other form of shielding there. Distance, not a lot you can do about. There's cosmic rays all around us when we're in interplanetary space and on the surface of Mars and the Moon. But shielding is the key thing, and shielding takes mass. That's why I'm so excited about the Starship generally, is that if it lowers the cost to orbit, there's a lot more we can do up there about taking things up that offer more shielding. But that's one thing that will have to be factored into the use of the mini-starship, for example. Water is an incredibly good shielding. If I had the ability to design a spaceship, I'd have some nice water tanks, whether it's clean water or waste effluent water, from the recycling system, and I'd have my crew habitation where people spend a lot of their time sleeping or working, within those water tanks. And that's how nuclear submarines help shield the crew. They have their nuclear reactor. They have quite a bit of space between that and the crew compartment, but then they put a nice bit of shielding in the way. Normally tanks of oil, tanks of water, other supplies, anything to keep a bit of shielding between that nuclear reactor and the crew. So yeah, I've seen a great deal on the various spaceship concepts, but shielding is one area that you can't just write it off. People tend to use charts saying, this level of dose is safe, but actually no dose is safe. There's always a risk. You and I at the moment, we're being exposed to cosmic radiation and background radiation, but we've evolved to adapt to it. Our bodies can repair it. As you go out into space, the radiation levels get higher. So we have to keep an eye on people's doses, and the NASA team at the moment do that very carefully with teams on the ISS. We need to monitor people's radiation as they head from A to B, from Earth to Mars, set some reasonable dose limits. What do we find is acceptable for people? And the final thing I guess we have to do is make sure that if the really big things happen, like a solar particle event where never mind, a year or 2 or 3's worth of dose, you can suddenly receive lethal doses in 10, 15, 20 hours. You need to have that built into the design to keep the crew safe as well.
Yes, I actually was thinking about that. The trip is planned to be 6 months long. because of the free return trajectory, which makes it a lot safer, not in terms of radiation, but also in terms of being able to return to Earth if anything goes wrong before the landing. I actually think it's a good idea to have the sleeping compartments be inside of the radiation shield for the solar flares. So even though that shielding is supposed to protect the astronauts in the event of an exceptional solar storm, I do believe it's still a good idea to have that be the place where people sleep, where the astronauts sleep, so that they're protected more from cosmic rays. So yeah, I'm not an expert in radiation, but yeah, that's what I think is a good idea.
That sounds great.
Yeah, I think that it's sensible. The solar particle event is the potentially life-ending event, whether it's a solar flare or a coronal mass ejection, and that's the one that if you're halfway between Earth and Mars, you need to be able to retreat into a solar shelter, ride out the storm, so to speak. Some spaceship designs actually deliberately angle the stern of the spaceship towards the sun as they're traveling, because you've got the bulk of the engines, potentially fuel tanks between the sun and the crew. And then that's a very sensible idea as well. If you're going to spend maybe 8 every 24 hours sleeping, having bunks or crew quarters actually inside that shelter is a good idea. A couple of good concept designs for the largest starship. Mike LePage, I think, had put a good video just showing how crew quarters could be set out, and he's actually envisaged using, for a 20-person crew on the larger starship, water tanks as that form of shielding. But yeah, anything you can do to reduce the dose. As I say, NASA sets lifetime limits on doses to crews, and a long duration mission to Mars, you would be pushing some of those lifetime limits. Unless you can carry out some other form of shielding and radiation reduction. And some of Angry's videos are excellent when you're talking about actually being on Mars itself, designing habitats. That was in the Mars Society presentations as well, that include some form of shielding, whether it's scooped surface material or having habitations inside lava tubes.
So while we're on the idea of safety, one thing that really interested me when I watched your initial presentation, Miguel, was the mission safety aspect of it. That actually out of 4 ships, only 1 was mission critical. Is there any chance you can expand a little bit more on that for the listeners and the members here today that weren't able to catch that presentation?
Sure thing. One of the key things I think need to be considered for a Mars mission is safety. And not just because of the astronauts' lives, which is obviously very important. When you have the astronauts there, they know what they're getting into, they know the risk that's involved in the mission. But also in terms of the mission they're undertaking. If we want to go to Mars sustainably, we have to show that it's safe. Imagine the whole world watching the launch of the astronauts or the Mars mission, which would probably be broadcasted all over the world. And then the people of the Earth see the astronauts die on Mars. Like the ship crashes, or if the ship crashes, there's nothing to do, but many other things can go wrong. So I thought, let's minimize all the things that could go wrong without going over budget. So the first thing is have the mini-starship land before the crew. An uncrewed mini-starship in the previous launch window and the bigger starship, one of each, would land on Mars without the crew. And if those fail, they do carry important materials and machinery for the mission, but the crew has not launched yet, so if any of those 2 fail, then something would need to be done in order to fix the ships. And it would certainly be a sad day, but the crew would not have left the Earth. So the architecture requires 4 ships, maybe 5. There are 4 elements, or some elements may require 2 ships. I haven't done a very extensive job of the mass requirements, but it should be around 4 or 5. So the first 2 ships be uncrewed and on the first launch window, so if those 2 crash or don't work, the crew would not have left the Earth. And then the 3rd ship is where the crew is. That ship is going on the 6-month free return trajectory, which means if anything goes wrong during the trip there, they can go around Mars and return to Earth. Then, if that ship lands, the last ship, which will arrive 2.5 months after the crew has landed, is not mission critical unless there's some big problem with the mini-starship. So if the last ship crashes, then they will not be able to use a long-distance exploration rover, they would not be able to mine ice, which wouldn't be a problem because I have rescued the concept of taking hydrogen from the Earth, so the astronauts would be able to produce the fuel for the first mission using just the Martian CO2, and the fuel would already be produced on Mars before the crew lands there. So yeah, I put a lot of effort into safety. But then if the crew lands far away from the first 2 ships, which is where the fuel is for the return trip, Then they can spend the first 1.5 months, which is what I call phase one, planting the flag, doing the first experiments and all that. And then the last ship to arrive can land next to it and deploy the rover, which they can use to go to the location of the first ships. And then they have the return trip there, so they can just move to the location of the first two ships and have everything they need to return to Earth. And then they would also, if everything goes well and the ice mining works, which is, I have put effort in making it so that they mine ice because it's the future for making Mars missions sustainable, but so that it's not mission critical. So they take the hydrogen needed for the return trip, they make the fuel for the return trip is made, and then they land on Mars and mine ice like if they were going to need it for the return, but they actually don't. They just produce more fuel, which could be used to firstly confirm that it actually works, and then if it works, they would just start storing fuel for future missions, which means that future missions would also have the return fuel already in place. So yes, I could not probably could not articulate everything on safety as well as I did in the presentation, but yes, I have put a lot of effort into safety. I even made a plan for how to survive a global dust storm without using nuclear power, which is something I have not seen resolved previously. And it's as simple as they have more than enough fuel for the return trip, so they would use fuel cells to produce electricity to run the key life support systems. So the only thing I could not fix, and I don't think it's possible, is if the ship in which the astronauts are going to land crashes, there's nothing that can be done there. But apart from that, I believe I have done a good job of limiting all the risks that could be solved without taking an amazing amount of mass and going over budget.
Yeah, I think your idea is pretty ingenious, and I think the best part is that people will most likely come alive out of it. But Angry, I would like to hear your opinion. Have you learned about Mars Direct?
Yeah, I've reviewed the proposal. It's most intriguing and has a lot thought through. I do have some questions. What is the wet and dry mass of this mini starship?
All of the calculations have been taken from Subrin's paper. If you Google Mars Direct 2.0, I believe you have a paper from Pioneer Astronautics, which is Subrin's company. And if you write the thing, it's obviously been written by him. And you have all the calculations there, except that in this case, you could make the ship a bit lighter by not taking that big of a heat shield, but you would probably compensate that with more cargo. So all the specs are over there. I was a student of aerospace engineering. I discovered it was not my thing. I'm studying economics and business management now because I like to specialize in the bigger picture. I like making plans. So I did everything I could in terms of the actual architecture, not on the actual details of the mission. But luckily, my proposal is not something entirely new. It's based on his work. So all of the hardware, the mass and the delta V has been calculated by him. So you can check out everything you want over there.
I'm assuming then that given that the Starship can only haul 100 tons to low Earth orbit, that the mini Starship would have to be taken up dry and then refueled in low Earth orbit. Without getting into any specific details, is that the principle behind it?
No, I don't think so. If I'm not wrong, Subrin said that the ship would be 20 tons dry and around 80 or 100 tons full of fuel, something like that. So the Starship could take the ship fully fueled to orbit. The thing is, he proposed two alternatives, which is, the first thing is the Starship just takes it to Leo, fully fueled, and then it goes to Mars, in which case it would be able to take a smaller amount of mass to the surface of Mars. But then he proposed that still inside of the Starship would be refueled on orbit, like it was in SpaceX's plan, to do almost all of the burn needed to go to Mars, just getting short of Earth escape, then deploying the mini Starship in translunar injection with more mass, and then going to Mars. I think that would be ideal, and SpaceX is still keen on developing on-orbit fuel transfer. So the mini Starship would still be quite massive.
Right, okay. So if it's 40 tons propellant to 20 tons, or I'm sorry, 80 tons propellant to 20 tons cargo, we're looking at about a 4-to-1 ratio of fuel and propellant, the same thing when you're talking about a chemical rocket, of course, but a 4-to-1 ratio there, whereas the actual Starship has theoretically 1,200 tons worth of propellant available to it to 100 tons. So you're looking at a 12-to-1 ratio there. So we're assuming we're assuming essentially that, the 4-to-1 ratio is what the original Starship is intended to go out with 1/3 of its tanks full in order to deliver 400 tons of mass to Mars. And I'm assuming that's probably what the 4-to-1 ratio or the mini-starship is being based on.
I actually just took his calculations and adapted them. I mean, in terms of numbers, I didn't change a thing. But there's one difference with the Starship and the mini-starship, which is, if I'm not wrong, the Starship would have its tanks full in low Earth orbit, and then it would do all the burn to go to Mars. But the mini-starship would depart from translunar injection in that version of the missions, in which case it would need a lot less delta V to go to Mars. And then it would leave a lot of its cargo on the surface of Mars, and when it returns from Mars, it would be lighter in terms of dry mass, so the fuel ratio would increase. But I cannot give the specific specs on that because, as I said, I try to focus on the big picture. If this is taken forward, there would need to be a lot of engineering put into it to make it more concrete, and I'm actually hoping that Dr. Subin jumps in and we can do a more revised and more concrete version in terms of numbers and specs. He has said the idea is interesting. I have not been able to speak to him in detail. But if for some reason this goes well, which I believe in the idea, I believe it's good. I was actually a bit skeptical at first because it has not been revised by too many people. But given the support that it's been getting, I am more confident that the idea, that I was not missing something, that the idea is good. So I hope he decides to jump in and we can develop a more finalized version and have all the numbers more precisely. But in terms of specs and delta V calculations, they are the same as for Mars Direct 2.0 in terms of the mini-starship. So I will look the paper that I mentioned before that Subin wrote in Pioneer Astronautics, and you can put it in the description for people to read it if they're interested in the specs.
The reason I'm asking these questions, I think some people who are familiar with my channel can probably guess why I'm asking these questions. I am highly speculative about the notion of using, the atmosphere almost exclusively to decelerate the Starship on landing. In my opinion, that represents the most dangerous aspect of this design, is assuming that the atmosphere, which is less than 1% of ours, is going to be able to decelerate the Starship sufficiently to where we can do a last-second engaging of the little bit of fuel that we have left, at an altitude of roughly 300 meters to decelerate to a zero landing. A question that I have, or just a thought that came to mind, is if the Starship could take the mini-starship all the way to Mars and then deploy its payload at that point, the mini-starship would have all of its propellant remaining for a mostly, or at least a powered landing once it hits subsonic. Once the atmosphere brings it to a subsonic speed, it would have all, or most of those 80 tons anyway, available for deceleration. And we wouldn't have to rely as much on the atmosphere for deceleration. What do you think about deploying the mini-starship, when we're getting close to Mars, as opposed to translunar injection?
That's actually something that Subin mentioned. He started watching the presentation a bit late, so I'm not sure if he presented it as, if he's asked it as something that he would like to be developed. But I don't see many advantages in getting the Starship to Mars. For starters, the Starship would be lost on Mars. It would leave the Earth dry and on fuel, or almost dry. Getting to Mars orbit would require quite a lot of fuel. And then, if you think about it, the mini starship in this architecture, and the one I'm proposing, would need that much fuel for for the trip to Mars, because it would leave from translunar injection, which is just short of Earth escape, which means at most it would do a burn of something like 1 kilometer per second of delta V. And then the rest would be free to land on Mars. Maybe a few meters per second would be spent on maneuvers on the way there, but then the rest would be free to land on Mars. It's not like you have your tanks already half dry or something, because you have spent almost the entirety of your fuel leaving the Earth, because you leave from translunar injection. So there will still be quite a lot of fuel available. The thing is, I base this also on SpaceX calculations, and SpaceX is confident that they can reduce almost all of the kinetic energy on the atmosphere, so I trust their calculations there. But as I was saying, there should be plenty of fuel for decelerating the descent. So you could probably double or triple the amount of delta V you have available for landing on Mars. So I don't see that as a big problem. But if you take the Starship all the way to Mars, you only have a mini-starship that has a bit more fuel, but then you lose the Starship. I don't see it offering any real advantage over here.
We actually were talking about aerobraking with AnotherSpaceNut and Benno on Deep Dive, so listeners, check it out.
Yeah, and there's a lot of interesting things that you've mentioned here, Miguel, about the technology to get us to Mars, the technology to sustain us on Mars, and then the technology to get us back. But there are always questions that come up about the why behind it. And I'd like to ask you, in your opinion, why do you think it's important for humans to make it to Mars and back?
Well, I'll answer with a rhetorical question. Why was it important for Europeans to go to America? Well, because if you have more places for human civilization to flourish, that has actually benefits for the rest of the human race. Centuries ago, when we lived in a zero-sum game, it would just mean that, alright, there would be humans in some other place. But we live now in the era of information, and one new invention can revolutionize the world and make the lives of the rest of the world a lot better. And information has almost no cost in being transported nowadays. And if you have more people and living in an entirely new environment, producing continuously new information, which will be the most precious good being transported from Mars to Earth, then it's going to be beneficial for the people living on Earth. Also, you have the possibility that the Earth might be destroyed. It's a very low chance that it will happen, like something like a meteor that destroyed the dinosaurs or a super volcano. But there's still a chance, and for what we know, there is no other intelligent life in the universe, so there's a chance we might be alone. And to run the risk of us being extinct, even if it's very low, I think it's quite dangerous. So as soon as we can start colonizing all planets, that risk will be greatly reduced. But also, it's very exciting. When we landed on the moon 50 years ago, it was a revolutionizing moment in human history. The whole world was united and excited about what had just happened. Countless people were inspired to become scientists and engineers, and some believe that that's what caused the digital revolution, or at least it accelerated it. And they were just stepping on the moon and coming back. The footsteps, the rocks from the moon being taken, but no big deal. Now imagine colonizing an entire new planet. It's like when America was discovered, the whole world, Europe mainly, was shaken. And from that point, new globalization changed the face of the Earth. A new continent developed in political systems that we didn't know of. A new superpower emerged, like the United States. And it undoubtedly made the whole world a better place. So if you reach a new planet, that's an opportunity for a new branch of human civilization to develop. And that's just the human aspect of it. Then there's the scientific aspect of it. Are we alone in the universe? If we find life on Mars, we could find out if life is a common thing in the universe or if it's not. We know that Mars was once a habitable place for life from some billion years ago. So there is a possibility that life has originated there too. We need to find we need to find out about that. And finally, the technologies that are developed for the Mars mission should be able to be shared for other industries, and that would have a great impact on other places. And it might actually be better than if those engineers had been working on something else, because when you concentrate many talented people into one goal, you make them work together, be motivated by a goal that's actually exciting, their productivity becomes greatly improved. So I believe that the result of this whole campaign would be beneficial in every possible way, unless of course there's a war for Martian resources, which would be unfortunate. Fortunately, Mars is very big, so I see the chance of that happening quite low, at least for the early colonization.
Does anyone else have any questions for Miguel before we start to wrap up?
I wanted to thank Miguel for his time, and it's great to hear a different approach. But I'll hand over to Angry because I know he's got his point to make.
I've made no less than 4 videos on, at least 4 if I remember correctly, and maybe 5 on what I call the SpaceX Starship suicide dive. Just indicating again how skeptical I am on the overall plan of using an atmosphere 1% of ours to slow down something that's that huge, when in the past we've required parachutes and sky cranes and things like that in order to reduce speed of a 1-ton probe, namely Curiosity, in order to safely land on the Martian surface. What I find very compelling now that you've explained this about this particular plan is if you can take the mini-starship to translunar injection, which would require, I'm assuming, at least 1 refueling. Per the Starship's own user guide, the Starship is only capable of taking 28 tons to translunar injection without a refueling. So you'd need like 1, I assume, refueling to get it to translunar injection. Then yeah, the mini-starship is going to have a lot more fuel available to it. And also, you're going to be dealing with a lot less mass as well when it's coming down through the atmosphere. So it makes the whole landing procedure, it sounds a lot more feasible to me, actually, when you have a lot more fuel reducing, less than 100 tons of mass as opposed to trying to reduce 200 tons.
Yes, exactly. And you also have one final layer of safety, which is having one ship land before the crew does, which is always good to have, even if it all works out in paper. To have an actual practical confirmation that it works is something that's very, very important to have in mind. But yes, having extra fuel over there is important, because the reason why the tanks would need to be able to hold so much energy would be mainly for the return trip, which would be from the surface of Mars to Earth orbit. That requires a lot more delta B than going from translunar injection to Mars, even landing on Mars. So that would partly be compensated by the cargo that would be taken to Mars and not return. That would partly be compensated by the more massive mini-starship that would go to Mars, because it would be loaded with more cargo, which would be left on the surface of Mars. But you could always sacrifice a bit of cargo just to be able to have more delta B available for a safe Mars landing, no doubt.
Great, thank you very much.
Thank you.
And that's it for this week's Becoming Multiplanetary. I've been RichLB, your host.
I've been Mikko, the host of Deep Dive Fridays, and it was really great to have you here, Miguel. Really insightful. And I'll pass over to Kage.
Thank you everyone for listening once again. I am Kage. And don't forget to check us out on all the various podcasting platforms, on YouTube from Total Space, and also on Twitter, TotalSpaceNut. And now I will pass over to AnotherSpaceNut.
Hi guys, I'm AnotherSpaceNut. Thanks for checking out this podcast today, and a big thank you to our guests, Miguel. A great honour it's been, and thank you for joining us today. Framric, thank you for coming on board as our in-house radiation specialist. And once again, thank you, Angry, for joining us for part 2 of Getting to Mars.
Thank you very much for the opportunity of appearing here again. Thank you, Miguel, for sharing all of this with us and for thinking outside the box. As anybody who follows the Angry Astronaut knows, I like to think outside the box when it comes to solutions. So until we have boots on Mars, stay angry about space.
Thank you to all of you for inviting me and from being here. It was great insight that you brought here. So again, if you hadn't watched the presentation, it should be on the description. And I'll also make a more detailed video when I can, hopefully before the end of the year. So thank you very much for listening. Please let us know in the comments if you have any questions or theories or anything that you'd like to share about Mars Direct 3.0. I'm still optimistic that this idea might be carried into the future.
I'd just like to say thank you for inviting me on today. Excellent episode, and I'm always happy to come back. Just let me know.
So that's a wrap from everyone this week. Please be sure to like and subscribe, and see you all again for next week's episode of Becoming Multiplanetary.